Here are the dogs.
I want to start showing you how actin network looks when it's in equilibrium. So what you see here is the typical actin-fasciin network characterized by these long and very straight bundles. And if you look at it in time, what you see is almost nothing. So they only fluctuate a little by thermal fluctuation. And if you want to see something as stable as that in cells, what you have to do is just kill them, so fix them, and then you see some stable structures like these contractile bundles. Margaret Ginell has told you this morning.
Sorry, what are the colors?
Sorry?
What are the colors?
The colors, so that's just fluorescence.
So what's stained red and what's stained yellow?
There's nothing staining yellow, it's just the lookup table modified to be looking like that, so it's just actin stable.
Okay.
So, that's what an actin network will look like in vivo. So here the actin cytoskeleton is stained by a peptide called LiveAct, developed in the lab of Roland Ludwig-Söldner. And what they found is structures they called actin worms. And these actin worms are highly dynamic, so if you look at a single worm, you cannot even follow it. So it will be destroyed, it will be built up, and moves to some other place. And what we wondered is how these highly dynamic structures can be built in vitro. So can we find a similar dynamic system in vitro? So what we're starting with is an actin-fasciin network. So that's the network you saw on my first slide. And so this network builds these very long and straight bundles. But even this network is not as stable as it looked like in the microscope, because these fasciin crosslinks are non-permanent. So they will eventually dissociate and perhaps even move to another place. But this won't lead to a reorganization of the network, because the actin filaments are just too large to move in time while the fasciin molecules are unbound. So in order to reshape a system like that, you would have to introduce some forces. And if you think about actin and forces, what you might think of is molecular motors called myosin. And these myosin minifilaments is like Jacques Pro had told you yesterday in the evening about contract your muscles. So we wonder what will happen if you just add motors in a stable structure like the actin-fasciin network. And what you don't want to see is drifting of movement of these filaments or bundles out of focus. So that's why we just confine our system in a very thin chamber that's spaced in 6 micrometers by adding beads. And another very important factor is that we have to passivate our surfaces really well, because else our whole system will just stick to the surfaces. They're so narrow together. So we put quite some effort to passivate these surfaces. So in all of the movies I'm going to show you, the filaments don't stick to the surface, but they are really in bulk in this 6 micrometer thick bulk. So what does it look like if you label your actin monomers and put actin and myosin together? What you see is you no longer see these very straight and long bundles that's typical for actin and fasciin, but they're much shorter. Their size is more heterogeneous, and there are even kinks in these bundles. And what's really fascinating most is when you look at it over time. So what you see is that a lot's going on. So here this bundle moves somewhere, and down there, and there should be something starting to move upwards here. Oh no, it's going down, and there's another one. So there's quite a lot going on. And if you're going back to the schematics, what we think will happen is you've got these myosin minifilaments, and they're pulling and pushing everywhere where they can stick to. But they won't be able to move they are in the muscle because they are held back by these fasten cross-linkers. So the movement of the myosin might lead to just build up of stresses, and if the stresses are large enough, it might even lead to disrupturing of the fasten cross-linkers and then binding these cross-linkers to different places like here or just nowhere like here. And so what you get is a disintegration, so you just disintegrate your bundles and they will move. And sometimes you can even see the stressings being built up in your network. So that's a zoom in of the movie I showed you in the slide before. So what you see here is myosin millifilament filament pushing or pulling here on this spot, I think, and this bundle will start to buckle, and then eventually just sorry, that's right. So it buckles, and then it's, at some point the stress is going to get too large right now, and it starts to move until it runs into another obstacle and where it gets stuck. So you can even tune how this network looks like. For example, if you add more myosin, that's what's shown here. So the first thing you see is that there are more bundles, but they are shorter, and I think that's because you've got more myosins, and so there's more stress to be built up. So the actin fasten bundles will get disintegrated much faster, so they're going to be smaller. But the disadvantage of this movie is you cannot follow these bundles by eye because there's just too much going on. So that's why we set out to quantify the movement of these bundles. And therefore, I wrote a correlation algorithm that first finds your bundles like that, and then it correlates it with the next frame and looks where it's going to. And as there are two reorganization processes taking place, so one is these bundles tend to move, and the other is that they reshape. So I follow where they're going to, and when I found them where they went in the next frame, I just readjust the box size. So that's what it looks like. And what you can do now is just follow a single box, and that's what you get if you see the trajectory smaller. So that's just on the y-axis how far a single box, so a single box is these colors, and has moved from one frame to the other. So that's just some kind of velocity. And if you look at a single box, what you see is, so at some point it starts running, then it stops, runs again, stops for a short time, runs again, and so on. And what's also a little bit, what you see is...
Sorry, is each horizontal line 0 for that box?
Yes. So
okay.
I just shifted them against each other. So what you see is there are some time frames where there's almost nothing happening. So if you go just up there, only few boxes are moving, but at others, for example here, there's quite a lot going on. So to visualize that, I just summed it up in this direction. And that's what you get. So and that becomes quite obvious that you have got some kind of burst. So there's sometimes there are many boxes are moving together like that, but at others, for example here, there's not so much going on. And you can see that a little bit better if you just bin your data. And yeah, that's what you see. So there really seem to be some bursts, and it might even be that there's a distinct frequency of these shifts of about 400 seconds. So that's 400 seconds. And so it looks like, but the data is just too noisy to really get a frequency out of it. So I don't see anything if I fully transform of that. So it's just I have to do much more work on that to see if there's a real frequency in there. So how could you explain that? So I'm sorry, I'm not able to simulate something like that, so I just draw some pictures. So the black spheres are actin filaments or bundles, and they're interconnected by fasten crosslinks that can be either relaxed, the black springs, or compressed, the red ones, or stressed, the blue ones. And on some of these bundles, what I didn't draw, there are some myosin motors pushing and pulling. So let's just look at that one and imagine there's a myosin motor pulling or pushing in that direction. So there's a force in this direction. What will happen then is that this stress fasten bond will eventually rupture. So that's what it looks like. And this rupture will then lead to lots of movements going on because that will then be able to move in that direction, but will lead to this bond to be disrupted, but that one can move in that direction. And so there's a lot of movement going on. And when you now imagine there are lots of myosin motors pulling or pushing simultaneously, what you'll get is, if you have a really stretched network, a single rupture event might lead to a whole avalanche of movements taking place in your network. And if the network is just relaxed, then it will take some time until you get these stresses being built up again. So that's what I think happens if you have these bursts, that you've got a stress network where where a single rupture event can lead to a whole avalanche of movements, while after such an avalanche you will have more or less more relaxed network that will lead to where you have only single clusters moving. So a similar system has been described years ago as being in a self-organized critical state, and consistent with that, we observe power loss in nearly every parameter we looked at. So that's, for example, the distribution of run length observed in the system. It's a nice power law. Or the stall time, that is the waiting time between two runs of a single box. So the only parameter that doesn't show power law behavior is the velocity, and I really like that fact because if you look at the maximum velocity of myosin 2 in skeletal muscle, that's about 1 micrometer per second, and I'm below that because I've got less ATP, so it's really consistent. So what you can say is that if you want to have really nice movies, just make sure the weaker bond gives in. So thank you.
Thank you. Questions?
So are the powers that you're getting consistent with some sort of percolation transition?
Actually, I don't know. So that's really preliminary data, and I haven't looked into great detail about it. So.
Is there a fine meshwork of actin and fasten behind these big bundles, or?
What kind of fine?
I mean, is there? I mean, you in the movies you see these very thick, coarse bundles, but is there a finer meshwork?
What I think is these really thick bundles. So I think these thick bundles are actin fasten bundles. They are bundled by myosin mini filaments together. So at least it looks like,
And what's in the rest of the space?
So in the rest of the space, what I don't see. If you have a really close look that doesn't come out on the screen here, is that there are some actin fasten bundles. Like here, for example, there should be one, and here's another one that you don't really see very well because there's a huge background. So here's really actin monomers labeled. So that's why your background is much bigger than if you label only actin filaments with colloidal, for example. So that's why you cannot see them. So there's some more than you'll see here.
In just the fasten bundles themselves, is there any polarity in the actin filaments?
Yes, there is. So fasten bundles are parallel. So the bar planes are on one side, and
so there's no mechanism for the myosin to change a single bundle. It can only pull one bundle against another one.
Yes.
You said that you went through great care to passivate the surfaces. How did you passivate the surfaces?
So I used denatured actin because there's a paper stating that the the best thing to passivate is something that's really close to the thing you don't want to stick. So that's why I use denatured actin, and then casein is in there. So.
Okay, with that, thank you. When asking questions, we want to be sure to have used the microphone for the webcast purposes. So our next speaker, we're grateful for having Professor Claire Yu from